The transformer architecture that powers all modern large language models is about to change. Imagine it's exam time and you are about to do some revisions. As a human, you probably won't go over every single word from page 1 to the end. But that's exactly how a transformer model works. Ingesting every piece of information with equal focus, meaning the same amount of computation is allocated uniformly across the input. In contrast, human will skim through the material, review the highlights from the notes, and spend more time on the topics that are more important or more complex. In other words, you take an adaptive approach, allocating more focus and brain power to where it needs most. This is exactly what we are going to talk about today: mixture of recursion. In 2017, Google Deepmind team has released a paper called Attention is All You Need. This architecture transformed natural language processing by relying entirely on attention mechanism, eliminating recurrence and convolutions. Now, what is recurrence? Recurrence refers to a method used in older neural network models, like recurrent neural networks, RNNs, where the model processes a sequence, for example, a sentence, one word at a time, step by step, in order. Transformer, on the other hand, instead of processing words sequentially, it uses self-attention to look at all the words in a sentence simultaneously, capture context without needing a step-by-step memory. This is like scanning the whole book at once to understand the connections between all parts instantly, making it faster and better for long sequences. Convolutions, used in the convolutional neural networks, CNNs, involve applying a small filter or window that slides over a sequence, like a sentence, to analyze a small group of words at a time. This filter looks for patterns like phrases or word relationships within its window and combines these local patterns to understand the sentences. It's effective for finding local connections but can miss broader context and require multiple layers to capture long-range dependencies. Transformer replace them with self-attention mechanism. Self-attention looks at all words in a sequence at once, capturing both local and long-range relationship without needing to slide a window. This is like reading the whole sentence at once with a wider angle lens, seeing all the connections instantly, which is more efficient than the magnifying glass approach. As you can see from here, in the abstract of this paper, we propose a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely. This allows the transformer to process entire sequences simultaneously, unlike older step-by-step models. The transformer consists of an encoder and decoder, each with multiple identical layers. You can have a look at this diagram. Each layer includes multi-head self-attention and a position-wise feed-forward network. Since it doesn't inherently understand sequence order, it uses positional encodings, like timestamps for each word. Think of a transformer as a factory with standard assembly line. Every part, whether it's a simple screw or a complex engine, goes through the same stations. It is efficient, but may overprocess simple parts. So, what is self-attention? Self-attention lets each word in a sequence consider all others simultaneously, capturing context efficiently. Unlike recurrence or convolutions, it processes the entire sentences in parallel, like wide-angle lens metaphor we used before, improving speed and long-range dependency handling. In December 2017, the DeepMind team introduced AlphaZero, which soon defeated world champion chess engines Stockfish, Elmo, and the 3-day version of AlphaGo Zero. In 2018, AlphaFold 1 and later the AlphaFold 2, an AI program developed by DeepMind again, has achieved astounding results in predicting accurate protein structure without any existing templates. So this transformer architecture became the bedrock of modern LLMs like OpenAI's GPTs and Google Bird, transforming the industries from healthcare to finance with smarter natural language processing (NLP). Your beloved Copilot, Grok, Gemini, or any other modern large language models that you know are probably based on the transformer design. However, although these models are powerful, intelligent, and brilliant, they are very power hungry and relying on scaling laws. More chips, more power, fueling giants like Nvidia. This high barrier blocks startups, driving the need for a more efficient evolution, a better transformer design. Now let's take a look at MOR. In July 2025, the same Deepmind team has released a new paper on the LLM architecture called Mixture-of-Recursions, learning dynamic recursive depth of adaptive token level computation. Now, what is recursive? Recursive refers to a process where a function or system calls itself repeatedly to solve a problem, reusing the same logic with different inputs. In MOR, recursive means using the shared stack of transformer layer multiple times for certain tokens, adjusting processing depth dynamically based on the importance. Think of recursion as a chef reusing the same recipe to make a dish multiple times, tweaking ingredients each time to perfect the flavor. In MOR, the same set of cooking tools, which is the layers, is reused to process important words more deeply, unlike the transformer's single-pass approach. Transformer is non-recursive. It processes all tokens in a single pass-through fixed layers, like a one-time trip through an assembly line, without reusing layers for additional processing. MOR is a recursive transformer. It reuses a shared stack of layers multiple times for selected tokens, with routers deciding how many recursive steps each token needs. As you can see from the abstract of this paper, we propose Mixture-of-Recursions, short for MOR, a unified framework that integrates parameter sharing, token level adaptive thinking depth, and memory efficient KV caching within a single recursive transformer framework. KV in this context as key and value. This enhances transformer strength with new efficiencies. One of MOR's key features is parameter sharing, reusing a shared stack across recursion steps to reduce parameters. MOR also uses adaptive computation, where routers assign different processing depth to tokens based on importance. As you can see from this figure, there are different routing strategies. MOR optimizes memory with selective key value caching, saving resources for long sequences. Picture MOR as a smart factory. It assesses each path, skips steps for simple ones, reuses machines, which is shared parameters, and caches pre-made components for efficiency. If we summarize the key differences of both architectures, the core difference is computation. The transformer processes all tokens equally, like a one-size-fits-all assembly line, giving every token the same attention, which can be inefficient for simpler words. MOR, built on the transformer, adapts computation per token, like a flexible factory tailoring processing to each part's complexity. Parameter efficiency is another distinction. The transformer uses unique parameters per layer, while MOR shares them across recursive steps. From this graph, you can see how the MOR models outperforming transformers with more efficiency, meaning using the less computation. Now you can have a look at this orange line, which represents the MOR architecture. And as you can see, the larger the model is, more effective this new architecture shows. Memory usage also differs. The transformer standard caching can strain with long sequences, while MOR selective KV caching, like recursion-wise caching, reduces memory traffic. While transformer is a powerful foundation, MOR enhances it with adaptive computation, parameter sharing, and efficient caching, making it more resource efficient for modern AI applications. So my title, I have to apologize, is a bit clickbaiting because the MOR architecture is actually the next evolution of the transformer architecture, which is based on transformer design, but better. So that's it for today. A quick comparison between transformer and the new MOR architecture. Now, if you are a machine learning engineer, I apologize, I cannot explain in more depth because I don't understand the paper. I should be watching your video and learn from you. And if you are a novice, try to get into the field and couldn't remember a thing I said, don't worry. The only takeaway you need to remember is all our modern large language models like ChatGPT, Grok, or Gemini are based on transformer architecture. Now we have a better one that's being developed by the same Google Deepmind team called MOR, which is built upon transformer design, but now better with adaptive computation. So that will make our model more efficient. Hopefully, more and more AI labs around the globe will produce new models based on this architecture, and hopefully they're open source. Okay, that's it. Thank you for watching. See you next time.